All right, we're going to look at one example now of a limiting reactant problem. So, as we've kind of seen before, we started off with Stoic talking about in ideal reactions how much of something could be made. Then we introduced the idea of, not all reactions are perfect when we talked about percent yield. And now what we're seeing is that in real life, you're not going to have you're not going to know exactly what amount of reactants to put together in a reaction. There's often going to be one reactant that's limiting or that runs out before the other one does. So the way that we can tackle these problems is first we'll read the problem. In an experiment, a mixture of 0.25 moles of methane is burned in 1.25 moles of oxygen in a sealed steel vessel. Find the limiting reactant. Alright, so the way that we can recognize limiting reactant problems, more than one amount given. You might have remembered in some of the Stoic examples, I would say reacts in excess this or reacts completely with this. But here we're not saying that, and you also know that there's more than one amount given in the question. So it's a really good clue for you that you're dealing with a limiting reactant problem. Our next step, just like with Stoic, is we need to write the complete equation. So we're going to assume that this is a complete combustion, just for the sake of the math, and because there's quite, like, in terms of number of moles, there's a lot more oxygen. So just keep in mind that this reaction would be entirely theoretical. So we know that methane, not CH4, is going to react with oxygen, and we know that it's going to form CO2 and water. Those are always the products of complete combustion. And then I'll just quickly balance them. Right, that's something that we've had lots of practice with. So what our next step is to convert all of the reactants to the same product. So we know that we have 0.25 moles of CH4, and we know that we have 1.25 moles of oxygen. So when we say convert all of the reactants to the same product, it means we're just going to have to set up two different equivalent proportion multipliers to figure out how much of one particular product would be created for each type of reactant if it were the one that was limiting. So to be able to do this, we first need to choose a product that we're going to convert it into, that we're going to set up our equivalent proportion multipliers to convert it into. I'm choosing CO2 because when we look at the molar ratio, we know that it's equivalent for methane and CO2, and that just kind of makes things easier for us. So the equivalent proportion multiplier there will be 1 mole of CO2 per every 1 mole of methane. And we know that's true because it says that in the reaction. This reaction would produce 1 mole of carbon dioxide for every 1 mole of methane that goes into it. And then we also need to convert the moles of oxygen into the same product. So if we go back to our reaction equation, we see that 2 is the coefficient in front of oxygen. So that tells us that the molar ratio and the equivalent proportion multiplier, the way we set that up is that in this reaction, you produce 1 mole of CO2 per every 2 moles of oxygen. And then we're just going to multiply those together to figure out how many moles of CO2 would be produced from each of those reactants kind of on their own if it were limiting. I know that I've set them up correctly because our units cancel out and we're going to be left with units and moles of carbon dioxide. So since that one was a 1-to-1 ratio, we know that if methane were the limiting reactant, we would get 0.25 moles of CO2. But if it were oxygen, we would get 0.625 moles of CO2. And then to be able to determine what's the limiting reactant, we just need to look for what reactant produces less of the given product that we chose. So 0.25 is a smaller number than 0.625, so that means that this equation here is going to give us our limiting reactant, and we know that it is methane. So we know that the methane produces less CO2, therefore it is the limiting reactant. At the same time, because we've identified methane as the limiting reactant, we also know is that O2 is in excess. So excess just means there's left over. So that means that in this reaction there's excess oxygen. And then even though I said at the start this reaction is entirely theoretical, like I'm making an assumption about what the equation is, I've now proven mathematically that oxygen was in excess. So we know that this was a complete combustion reaction. So that's how you determine the limiting reactant. And I'm going to leave this example here for now because you might be asked in a question to determine how much product is actually formed. So to say, in the reaction, how many moles of CO2 are produced? How many moles of water are produced? What's the mass of water that's produced? And once you determine what reactant is limiting, then you determine how many moles of the other products are made, and from there you're just performing stoichiometry to determine how much product would be formed. So I would leave that up to you because we've already seen plenty of examples of stoichiometry.